All right, honor stats. This is the last section of Chapter 8 dealing with estimation. And in section 8.3, we're going to be estimating P, which is the population proportion in a binomial distribution. Okay, so please remember our population proportion P. If you think about it, if you choose a sample and you're trying to find out about everybody, that's what the P is. All the people, okay? We're going to compute the maximal length of error for proportions using a given level of confidence, all right? So margin of error, little different formula. We're going to compute confidence intervals for P and interpret the results. So if you think about chapter 8.1, mu was our interval. In chapter 8.2, mu was our interval. And now chapter 8.3, P is going to be our interval. We are not going to interpret polls, so if there are any homework questions dealing with that, no big deal. And we will end up with computing a sample size, okay, that we will estimate to find our P. Okay, so we're going to have a couple different formulas for this section, but when you read the problems, it should jump out at you as being a P problem and not a mu problem. Okay, so finishing up, understand that we found the maximum length of error. We found E, new formula. We computed a confidence interval for P. We did not interpret polls, and we computed a sample size. All right. So please understand the difference between 8.1, 8.2, and now 8.3. 8.3 is the one that's the most different. You're finding P instead of mu. All right, so that's the end of chapter 8. Here's the only criteria that you need in order for these problems to be normal. N times P must be greater than 5, and N times Q must be greater than 5. Once those are met, then it's a good approximation to a binomial distribution. In our previous two chapters, 8.1 and 8.2, we used X bar as a point estimator for mu. And if you think about it, remember you had X bar plus the E and X bar minus the E. So that was 8.1 and 8.2. Well, we need our point estimator for P. And the point estimator for P, everybody, is P hat. So now we are going to be having P hat plus our error and P hat minus our error. So this is going to be our interval, which we'll look at in a moment. All right, but understand where P hat comes from. All right, we'll look at that right now. P hat, ladies and gentlemen, is R, the number of successes, over N, the total number of whatevers. So if we have 150 people and 100 like cheese pizza, well, the 100 that like cheese pizza is your R, it's your success, and the 150 is the total number of people. The P hat, as you know, is a proportion. You simply plug it in your calculator and give me a decimal for that answer. So P hat is our sample proportion. Q hat, everybody, is 1 minus our P hat. So once your P hat is given, then you can find Q hat. This, ladies and gentlemen, is your Bible for section 8.3. The first thing, please understand that P hat is going to be found by you. It's taken R, the number of successes, divided by N, the total number of whatevers. You can also find Q hat by subtracting 1 minus our P hat. Understanding the number of trials are sufficiently large enough if N times the P is greater than 5 and N times the Q is greater than 5. Once those criteria are met, the data is normal. So let's take a look at our confidence interval. Our confidence interval is going to be for our population proportion. We're going to use our point estimator, which is our sample proportion called P hat. And we are going to add and subtract our margin of error. Well, guess what? Margin of error has a new formula. And here's the formula that you have to memorize. Z of C. Same as what chapter? 8.1. Those are your memorizations. 90 is 1.645. 95%, 1.96. 98%, 2.33. 99%, 2.58. Plus you have the ability to find any other one by drawing the curve and doing a little bit of work. So Z of C, P hat and Q hat will be, in a sense, given to you, and N will be given to you. And don't forget to take the square root. So that's how we find our margin of error for a proportion question. So let's do a problem in its entirety. Suppose 800 students were selected at random from a student body of 20,000 and given shots to prevent a certain type of flu. So in this case, everybody, the 20,000 is your population. Okay, we're not talking about everyone in the world or everyone in the United States. It's at this particular place, 20,000. But guys, you don't want to give the flu shot to 20,000 people. You want to do a sample. So what they did is the 800 students that they sampled were exposed to the flu and 600 did not get the flu. So the 600 is our success. So you should know that N is 800. 800. R is 600. That means the flu shot worked. So with that information, we can find P hat. P hat is R divided by N. We can reduce that to 3/4, which is 0.75. Therefore, Q hat is known to be 0.25. Let's do our test. N times P, or N times P hat, and N times Q hat. This is going to be 800 times 0.75, which we know is 600. And this is 800 times 0.25, which is 200. Both are greater than 5. Therefore, the data is what? Approximately normal. So there's no way for me to white out this particular work, so I'll just kind of walk through. Their question is, we want a 99% confidence interval for P. And as soon as you see that, it's not mu, it's P. That tells you it's an 8.3 question. So here's our formula. There's our Z of C, which deals with the 99%. Here's P hat, here's Q hat, here's N, and there's a big old square root. You must memorize that the Z score, Z critical value for 99% is 2.58. We found our P hat to be 0.75, our Q hat to be 0.25, and N is 800. Now, just to make sure, when you plug this into your calculator, I would do this piece first. I would type in my square root. I would type in my numerator of 0.75 times 0.25 divided by 800 and hit enter. And while that answer's in my calculator, hit times 2.58, sorry. Now, I agree with the book that you guys have to remember that section 8.3, these guys have to go to 4 decimal places. And I'll tell you why. Being that we're dealing with P now, P is a percentage. P is a decimal. So normally, you got that 0.75 is what we're going to be manipulating here in a second. We're going to add and subtract to that P hat. If you think about it, if you move it 2 decimal places, you're just talking about 75%. I want 4 decimal places. I want it more precise. I want 75.28%, etc. Okay? So let's finish this guy up. P is in between our P hat plus our E that we just found and P hat minus the E we just found. Well, P hat is the 0.75, and we're taking away the 0.395, 0.75, and we're adding the 0.395. This will be my final interval here. So subtraction gives me 7105. The addition gives me 7895. So now when we do this explanation, the interpretation, I am 99% confident that the true population proportion P is in the interval from 71.05% to 78.95%. So hopefully you can see why I want 4 decimal places. It just sounds better, 71.05, 78.95, instead of rounding it to whole numbers. Okay? So this, ladies and gentlemen, is how to find a confidence interval for the population proportion. Okay? So in a sense, everybody, there's 20,000 people that are in that school or wherever they were at. The true proportion that this drug will work on, meaning they won't get the flu, is somewhere between 71.05 and 78.95. And so funny, if I said how many people would that be? Between how many people are not going to get the flu? What would you do?
That percentage times 800.
Yeah, if you just simply multiply this to 20,000 and multiply this to 20,000, this is one of those questions that I would put on a test, and you guys would be like, "Oh, you never went over this before." But so if I take 0.7105 and I multiply it to 20,000, it gives me 14,210, and 0.7895 times 20,000 gives me 15790. And that's our X. X is people, data people in this case. So somewhere between 14,210 and 15,790 people will not get the flu if they get the shot. Make sense? So we just added a little bit more to this example. And now, selecting the appropriate sample size for estimating a population P. You have 2 formulas to memorize. If I give you a preliminary estimate for P, meaning somebody has done a study somewhere down the road and we're going to use that data to help us out, your problem is going to be P hat times Q hat times Z of C divided by E squared. I have to give you E. I have to give you the confidence interval percentage so you can find the Z sub C. And then I'm giving you the P hat. That's what it says. There's a preliminary estimate. But if I do not have one, then you have to assume, remember, this is still actually P hat and Q hat. But why is there 1/4 there? Because if you don't know what the true proportion is, sample proportion P hat, then you have to assume there's a 50-50 shot of getting a P or a Q. Well, what's 0.5 times 0.5? 0.25 or 1/4. Okay? So you need to memorize this formula. Example of the first. A company is in the business of selling wholesale popcorn to grocery stores. The company buys directly from farmers. A buyer for the company is examining a large amount of corn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, the probability a kernel will pop. Suppose a random sample of N kernels is taken and R of these kernels pop. So notice they didn't give you any of the numbers. So the buyer wants to be 95% sure that the point estimate for P hat is either more or less than 0.01. That's your error. Now, they did not give you any preliminary study. All right? Think about it, guys. Are you going to pop 10 kernels of corn, heat them up and pop them? What if all 10 pop? You can't say, oh, 100% of my kernels will pop. Or you can't go in reverse. You can't take 2 million kernels and pop them because you're like, oh, I want to pop as many as I can. Well, you just wasted your entire product. You see what I'm saying? So we want to know the true number. And in this case, it's going to be 1/4 because it was not given to us. 95% Z is 196. The error is the 0.01, and we can't forget to square. So I would take 1.96 divided by 0.01, hit enter, which is 196. I would square that and get a big old 38,416, and then I would multiply by 0.25. And this gives me an exact whole number. Kernels. There was no decimals here. Okay, there was no decimals. But we know when we look for a number of something, everybody, when we look for a number of something, you always round what? Up. This happened to be exact. So if you know nothing about these kernels, if you choose 9,604 kernels and pop them and see how many pop and how many don't pop, it will help you find the true population proportion. Look, same work. But now, a preliminary study shows that P was approximately 0.86. So somewhere down the road, somebody did a study, and the owner of this corn says, you know what, 86% of my kernels pop. So now they've given us a number. So if you are doing a study, you want to find out how many kernels to choose. Notice, everybody, it's given to us. So there's our P. That's our Q. It's still going to be 95%, so 196. And it's still the, oops, I don't know why I put a square root. Sorry about that. My head was on the other formula for some reason. Squared and 01. So 1.96 divided by 0.01 square. This time I'm going to multiply by 0.86 times 0.14. It spits out 4625.29. Everyone, what is the answer? 4626. Okay. Now, if you remember, the answer before was larger. right? The values for P and Q. The largest N that you can ever get is when it's 50-50, 0.5, 0.5, that 1/4 that you multiply by, okay? But if we have a preliminary P, we can use it to help us find the number of kernels that you should pop and see how many actually pop and don't pop. Okay, those are our values of N.